Okay, let's take a look at question 1 from the 2011 scholarship paper. It's the first thing I did with this paper now was I scanned through the whole paper and just to verify how many questions there are, because it can vary from 5 to 6, but it tends to be 5 since 2011 at least. And then I took a look at the different genres or categories of questions that you have, just to identify the core content that's being assessed. So this first question, they're talking about particles and sizes of atoms, and then I've just a double page screenshot here. So the second part is also about trends in the periodic table. So this is definitely structure and bonding stuff, and from level 3 mainly, from what I could see from the question. So the first part of the question, the key thing with structure and bonding is the use of key terms, and this is the same for the topic in level 2, which makes it quite difficult to mark, so, and also to write questions which pick up marks. Okay, so let's take a look at answering this question then. Question 1, part 1. Discuss how the charges on subatomic particles contribute to the size of atoms and their ions. Now I know this is a part A of the question, so typically part A's tend not to be as involved as the part B's, and I've learned that from doing the first paper, the 2012 paper. So I'm just going to sketch down some key ideas here, and then we can take a look at the NCEA written answer for this, because as I say, there's a lot of text and I don't need to be writing it here. I just need to highlight the key terms and maybe give a bit of explanation. So the subatomic particles, as you would know from level 1 or even before that, charges we're interested in here. So we're talking about protons, which are positive, electrons, which are negative, and neutrons have no charge, neutral, so we don't really have to consider them in this answer. So we're talking about the relationship between proton number and electron number, and the size of an atom or an ion. You can also talk about atoms and ions in separation, because they are two different particles, and the charge has a large effect on the size of the ion. We're also going to try and relate to part 2 here, because I have the page open, and it also tells you to relate your question, your answer from part 2 to your answer from part 1. So what do we need to talk about here? Well, the general trend in the periodic table is, as you go across from left to right, we have the atomic radius should decrease. Atomic radius decreases as you go across the periodic table, and the atomic radius increases as you go down the periodic table. So atomic radius increases, and this is a decrease, so you would start off large and then getting smaller. So why is that? Well, as you go across the periodic table, we're increasing the number of protons. So if you increase the number of protons, you effectively make the nuclear charge, or the nuclear positive charge, stronger, which is referred to as the effective nuclear charge, or ZF. So that's the effective nuclear charge. Okay, so if you increase the number of protons, you increase the effective nuclear charge, and therefore the electrons should be pulled closer to the nucleus, and the atomic radius decreases. And this happens as you go across the periodic table. And you have some numbers there. The numbers, the dark circles represent ions, and then the grey ones represent atoms. So if we have 152, that would be the atomic radius. 152 picometers would be the atomic radius for a lithium atom, and then it decreases to 111, then 70, 66, and 64. So that's a trend in atomic radius decreasing as you go across the periodic table, and that's because the number of protons is increasing. Conversely to that, as you go down the periodic table, this situation here, your 152 increases to 186, to 231, and 244. So the atomic radius increases down a group. So it decreases across the groups, or the periodic table, whereas it increases down a group. And this is for a few reasons. First of all, so the proton number of protons is still increasing, but you're also adding more electrons which you'll have electron-electron repulsion. Okay, so like charges will repel each other, so the more negative charges you add in there, the more electron-electron repulsion you will have. And then the other thing you have is you're adding electrons in shells which are further from the nucleus. So as you go down the group here, you are adding shells. So this would be shell number 2, hydrogen, helium, or shell number 1, number 3, number 4, number 5 for rubidium. You're in shell number 5, so the electrons are physically further from the nucleus. Therefore, the effective nuclear charge on those particular outer shell or valence electrons is much reduced. The other thing you want to always talk about here is electron shielding. And students often think this is a difficult concept, but it's essentially the idea that as you have successive shells, if this is shell number 2, 3, 4, the more electrons you add, the more of a shield or blocking effect you create on that positive charge of the nucleus, and then these electrons are blinded or shielded from the charge of the nucleus by the previous shells before them. So shielding, electron shielding, is very important to mention as well. In terms of ions, well, the situation with ions is, and I'll just continue this over here, with ionic radius, group 1 elements, because they have one electron in the outer shell, they lose one electron. And if you lose one electron, then you have one more proton than an electron. If you remember, atoms are neutral, so therefore you have equal numbers of protons and electrons, which you get from the atomic number. So as soon as you remove one electron, you have an excess of positive charge, so the effective nuclear charge increases, and the radius, atomic radius, will decrease. So if we take a look at that for a group 1 element, so we can delete one of those numbers for a second just so you can see that. Alright, so for lithium, the lithium atom, the atomic radius is equal to 152 picometers, and that's from right there. And then, whereas if you form a lithium plus ion, the atomic radius is equal to 60 picometers. So the atomic radius has decreased there quite significantly, and that's because you have removed one electron, and the effective nuclear charge is increased. Conversely, if you go across, so if you go across the groups with ions, the group 2 ions, similar situation to group 1, so we don't need to talk about them. So as I say, group 2, same scenario. If you start off with an atomic radius of 111 picometers, and then you remove 2 electrons, so then you're dropping in a shell, then the radius for the ion, or the ionic radius, is 31 picometers. But if you go to the right-hand side of the periodic table, as well as atomic radius decreasing, electronegativity of the elements increases as you go from left to right across the periodic table. And this means these atoms prefer to gain electrons as they ionize. So if you take something like oxygen here, oxygen, the atomic radius is 140. So the atomic radius of an oxygen atom is equal to 140 picometers, whereas the ionic radius of O2 minus, which has gained 2 electrons, is 66. This is because, let me check if I have those numbers correct. So the dark circles represent ions. So I have this the wrong way around. I knew that didn't make sense straight away when I wrote it. So the ionic radius for O2 minus is equal to 140 picometers, whereas the atomic radius is equal to 66 picometers. So you can clearly see a jump in size as you added those 2 electrons. And hopefully that's easy enough to explain for you. When you add electrons, so from oxygen to O2 minus, you're adding 2 electrons, which means you have 2 more electrons than you have protons. So you have an excess negative charge. The other thing you have is an increased shielding effect, and therefore the effective nuclear charge is decreased, and so the ion increases in size. So you could easily use any of the other elements from that table and to explain your answers. It is only a part A. It is only a part A question, so you shouldn't be spending too long on it. Now let's just go through the NCA answer just to see if I skimmed over anything there a bit fast. So if we look at part 1 and part 2 together here, I'm just going to highlight some key terms that you must have included in your answers to cover this question. Electrons are negatively charged, so you needed to mention the charge, and protons are positively charged, and they're in the nucleus. The force of attraction is proportional to the size of the charge in the electrons. Electrons are always -1, and the charge in the nucleus, which increases with an increasing number of protons. The force of attraction also depends on the distance between the electron and the nucleus. The greater the distance, the weaker the attraction. We can underline that. As the valence electrons are found in energy levels further from the nucleus, the force of attraction will decrease. That makes sense. Electron-electron repulsions cause electrons to maximize the distance between them. So you wanted to mention electron-electron repulsions. Electron-electron repulsions between valence electrons and core or inner electrons reduce the effective force of attraction between an electron and the nucleus. This is commonly known as shielding or screening. So we mentioned that. Scroll on down. When a cation is formed, the outer layer of electrons is lost, so the valence electron is close to the nucleus, increasing the force of attraction and decreasing the radius. We covered that. And you want to use an example from the table just to substantiate or back up your answer. When an anion is formed, an extra electron is added, and in order to minimize the repulsion between the electrons, they move further apart, increasing the atom size. So I suppose my explanation for the anion increasing in size mightn't have been as good as that. So with anion formation, it's the extra electrons repelling each other that causes the ion to increase its size. In part 2 here, size of atoms across a period, electrons are being added to the same energy level and the nuclear charge is increasing because you have more protons. So nuclear charge due to more protons is increasing as you go across the periodic table. The increased nuclear charge causes the electrons to be attracted more strongly, so the size of the atoms decreases. Down a group, the electrons are in energy levels further from the nucleus, so it's distance from the nucleus, with increased shielding from inner shell electrons, which means that the size of the atoms increases. So that's kind of reiterating what we already said for part 1. And then size of ions. Across a period, the size of the ions initially decrease in size. Although the cations are isoelectric, the increased nuclear charge across the period attracts the valence electrons more strongly, so the size of the cations decreases. And that's because you've lost 2 electrons, so the nuclear charge is increased. Ions on the right are anions. That's because of being more electronegative. More electronegative. These will be larger than the cations to the left of the period, as the added electrons means that they have an extra energy level. Okay, similar trend is seen. Okay, this is a little bit about trends there. Relationship of size of anions and atoms is caused by the repulsion of the added electrons. Relationship of the size of cations and atoms is caused by the removal of an energy level, the reduced distance between the valence electrons and nucleus, and the reduced effective shielding. So it's quite wordy, as you guys know from structure and bonding, but the key thing is to get those key things which have been underlined there, and then use examples from the table that you were given, and that should be enough to get the marks for that answer. Okay, so part B of question 1 from the 2014 paper. I read through this, as I say at the beginning, and the first thing I wrote down for this question was that this was a level 2 concept, and it was all about equilibria, position of equilibrium. So that we're talking about Le Chatelier here, and Le Chatelier, if we just remind ourselves, Le Chatelier says that a system will respond to a change by undoing the change to the system. So, for example, if you increase the temperature, the system will try to decrease the temperature, do whatever it needs to achieve that by undoing the change to the system. So let's take a look at the question, the particular scenario that we have here, but that was Le Chatelier. So we just want to recognize the guy that came up with this concept. So the Boudoir reaction is the name given to the oxidation reduction reaction involving a mixture of carbon, graphite. Now we know graphite is just solid carbon, so that's solid state carbon dioxide, which is gaseous at room temperature and pressure, and carbon monoxide. All right. Now room temperature and pressure, I know you have atmospheric pressure, which is the same as 1 atmosphere, or 101 kilopascals. So we know it's at atmospheric pressure. The temperature is varying, but those molecules are still gaseous. So this is your equilibrium. So this was another giveaway that this was an equilibrium question at a given temperature. So this graph also is an equilibrium graph, because you can see that at certain temperatures you have one gas present, and at another temperature range you have another gas present, and then the two intersect at a point here, which is a sign of an equilibrium reaction. The particular reaction we're looking at here is that carbon is reacting with carbon dioxide gas, and it's an equilibrium, so you put in your equilibrium arrows, and then you get 2 moles of carbon monoxide gas, and just make sure that's balanced. So that's the situation. So all of this stuff is reacting inside a blast furnace, which is used for separating different metals, in this case, from their metal oxides. So this is just the context. So the graph below shows how the reaction mixture composition of the gases present changes with changing temperature at atmospheric pressure. So the changing temperature is the independent variable. The atmospheric pressure is kept constant, so we're only varying one thing here. And then the question states, part 1, identify with justification the product of the exothermic process in the Boudoir reaction. So it's an exothermic, so we look for the species which is going to be present if it's an exothermic process. So if we look at our graph now, an endothermic process, by definition, if something is endothermic, you put in heat, so you add heat, and you will get more of the product species. Now the product species in this case we're saying is the carbon monoxide. And if you look at our graph, as you increase the temperature beyond 1000 degrees Celsius, we get more carbon monoxide. So we're saying the forward direction of this reaction, this equilibrium, is requires heat. If you have more heat, then you get more of the carbon monoxide. So more heat will give you more carbon monoxide. And then by default, then, if the forward process requires heat, then going in the opposite direction must be exothermic. So the production of carbon solid and carbon dioxide is exothermic. So they're the products. So the products of the exothermic process, as we're being asked here in part 1, will be carbon solid and carbon dioxide gas. Now the way I used to teach this with level 2, just to give a bit of structure to your answer, there's always going to be a change to the system. So our system is the mixture of carbon solid, carbon dioxide gas, and carbon monoxide gas inside the column, the blast furnace. Right, that's our system. And the change to the system here is that we have increased the temperature. In this case, we're increasing the temperature. So if you increase the temperature, the system wants to undo the change, so it wants to decrease the temperature. And it does this, achieves this, by producing more carbon solid and more CO2. Because then it okay, so let's just make sure I'm saying this the right way. So as the temperature increases, you want to decrease the temperature, and the decrease in temperature favors the production not of those two there, but of the carbon monoxide gas. Okay, and the answer itself is a bit confusing when you read it first, but it is correct. So That's what happens with that change to the system. The second part of the question is use your answers to discuss the reaction products when the hot gases from the blast furnace reach cooler air. So the change to the system here, change to the system is that you're decreasing the temperature. So if you've decreased the temperature of the surroundings, you want to increase that temperature again, so the equilibrium will shift to the left-hand side, which is an exothermic process, and therefore you'll produce more carbon solid and carbon dioxide gas. So let's just repeat that again. This is essentially the guts of your answer right here. If the temperature is increased, you want to decrease that temperature, and you achieve this by producing more carbon monoxide. And if the temperature is decreased, you want to increase the temperature of the system and the surroundings, so you shift to the left-hand side because that produces carbon and carbon dioxide, which is an exothermic process. So that's the justification for part one. We can take a look at the answer here. It's quite short. There's the equation, so we got that right. Lower temperatures favor carbon dioxide. As temperature increases, more carbon monoxide is formed because it's an endothermic process. So exothermic reaction favors the formation of carbon and carbon dioxide. When gases reach the top of the smokestack, they will cool down, so the equilibrium reaction will move to the left to generate more heat, which is the exothermic process, and this will favor the production of more carbon and carbon dioxide. Now the last part, you can already see how short it is, the answer to part two, but it's short and easy if you can understand how to do it, and I certainly was stumped, I have to admit, for the first few minutes. Okay, so let's read through the last part of question 1, part B, and this is the part 2. There's a lot of detail again, but the answer is very short, as we just saw. A large heat-proof syringe with a freely movable airtight piston initially contained 50 mils of carbon dioxide at that 1 atmosphere or 101 kilopascals pressure and 25 degrees Celsius. So we can illustrate this with a little diagram or picture. So there's your syringe. You have a plunger inside, so it's a closed system because you have gases. You have that with a dot, and then the rest of the product, which is also equivalent to 50 centimeters cubed of gas, and that's of CO2 initially is all we have. So we have our two from our equilibrium equation. Then there's a certain temperature we don't know, that mixture is heated to. So heating temperature, X degrees Celsius, we don't know. And this is what we need to find out. Determine the temperature at which the reaction was carried out. The product, the situation then, the apparatus was heated and maintained at a certain constant temperature until equilibrium was reached. And the equilibrium we're looking for is carbon solid plus carbon dioxide gas going to 2 moles of carbon monoxide gas. The apparatus was then cooled rapidly to 25 degrees Celsius. At this temperature, any further change in composition was negligible. So we're assuming that whatever amounts of carbon dioxide and carbon monoxide we formed are still there. And at the end, a total volume of 60 mLs of gas was present. So we end up with an increase in volume. So let's just represent this by this is 60 mLs right here. So we've an increase of 10 ml. And the question is, if the same conditions apply to this experiment that are represented by the graph in the previous page, so we need to use the graph from before, and the graph, we'll take a look at that towards the end of the question. The volume of the substance in its gaseous phase at a particular temperature and pressure is directly proportional to the amount in moles of the substance present. So this is the trigger. Because if you look at the moles of each substance present, we're told that we start with 50 mLs of carbon monoxide. There's only 1 mole there, so 50 mils for 1 mole of CO2. We don't know the volume of carbon monoxide formed, so we just do 2x represents the volume of carbon monoxide formed. This is using this statement here and our equation, our equilibrium equation. So we have 2 moles. So at equilibrium, 2x, it represents the volume of carbon monoxide formed. So the situation we have here, and the volume of CO2, we can write an algebraic expression for that. Volume of CO2 is going to be that original 50 minus x, because you're going to use up some of that CO2 to produce your carbon monoxide. So we know the final volume is not going to be 50. So it's 50 minus x. So then the equation becomes 60 ml, which was your final volume. And the 60 ml we just wrote there. So you're at the end, you have 60 mLs of gases, and that's going to be CO2 gas plus your carbon monoxide gas is equal to 2x plus your 50 minus x. So remember, this represents your carbon monoxide and this represents your carbon dioxide. And then if you work out that little equation, you get a volume of 10 ml will be equal to x. Okay, so since the volume of carbon monoxide was equal to 2x, your volume of carbon monoxide at the end is 20 ml. And then since your volume of CO2 is 50 minus x, then that's equal to a volume at the end of 40 mLs, and that adds up to give you your 60. Now the little catch is that 20 mLs represents 1/3 of a volume of carbon monoxide versus 2/3 CO2. And if you read that from the graph then, and we're just going to skip up to the graph. So up we want to go. So back of the graph then, 1/3, which is here, brings you to about that point in the graph, and then 2/3 brings you to about this point in the graph. So you're talking about somewhere in between here and here, which is about a temperature of 475 to 485 degrees Celsius. So that's the temperature that they were looking for to achieve those particular ratios of gases. And then you can see that answer is covered here, nice short detail. So question 1 on this paper was actually not too bad. Having said that, if you didn't know how to do that particular bit of algebra, then part 2 you would never have known where to start. But put the stuff down in paper. Anyway, that's question 1 from the 2011 scholarship paper.